I look forward to coming here every year. This is my third year. And when I was younger, I used to do a lot of talking at schools and stuff, and that was always a lot of fun because it was typically at schools that somebody would always ask me a question that I really couldn't answer. You know, when I go talk at a technical meeting, they always ask me a question about my research, and I always got the answer nailed. But kids usually could come up with something. Early in my career, mostly it was about how the toilet works on the shuttle. That was the standard question, so I always had the answer ready for that one. It's a very interesting time at NASA because fundamentally anything we do in space is really expensive. It's just really expensive. And I'm sure you're all aware enough that spending on anything by the federal government is kind of a problem these days. And so things that are expensive and don't get you a vote typically don't make it into the budget very well. So NASA's undergoing some pretty significant kind of tumultuous changes the last couple, 3, 4, 5 years, trying to figure out how we can keep doing what we've been doing, but without spending anywhere near as much money on it. And the people that have been working at NASA for a long time, they like to do things the way they've always done it, and it's very difficult to get people to change. I've always worked in an area that there was always something new going on, so I'm kind of used to things changing. But a lot of people really get very resistant to change. So about 5 or 6, well, I guess it's 7 years ago now, I got interested in trying to address this question about how can we explore space sustainably without it being so horribly expensive. And the last couple of years I've come to this event and talked about specifically how we can figure out ways to live off the land when we go to the moon and to Mars. And there really are some technologies there that would make that possible, but we're going to need, we need money to figure out how to develop those technologies. So there's this real challenge going on to figure out how to do this. And the other thing I wanted to mention at the beginning is that the thing that is the most new at NASA these days is the idea of actually turning over some of what we do to industry. Can you imagine what it would be like if, the Wright brothers flew the first airplane, right? We all know that. Pretty much immediately after that, the only money that was available to take it past flying for 12 seconds at Kitty Hawk came from the government. Okay, so the government funded all the work in aviation development for a few years. Can you imagine what it would be like if the government was still completely in charge of aviation? You wouldn't be able to get on an airplane. There would be, airplane-anauts. They'd get to fly from here to New York, but you wouldn't be able to. So, very quickly, private industry took over the aviation industry, and look what we have today. NASA has really been very resistant to do that for a bunch of reasons. First of all, launching in a rocket, it's really dangerous. A lot of things can go wrong. In the Space Shuttle, there were 5,000 things, there were in excess of 5,000 things that could make the shuttle fail in every launch. 5,000 things they had to keep track of, and that's why it was very expensive. You had an army of thousands of people keeping track of all of that. We can't afford that. If we're going to do any space exploration, it's got to be cheaper. So one of the things that's going on now, and there's big arguments in Congress and at NASA, is how do we turn this stuff over to private industry? So there are some examples that are starting to happen now, and I'll mention a couple of them when I get into the talk. But we're really at, what I want you to think about is, don't think of NASA the way perhaps you've thought of it in the past. Think of it a few years in the future where a lot of what's going to happen is not going to be done by somebody that gets a paycheck from the federal government, but gets a paycheck from a company that you probably haven't even heard of yet, because that company may not even yet exist. There's Boeings, and there's Rockwells, and there's Lockheed Martins, and there's a lot of big aerospace firms, and they're certainly competing in this. But a lot of the innovation, the first commercial cargo ship to send something to the space station is going to happen this month. They're basically being paid to deliver cargo to the space station. It's a company called SpaceX, and they had one successful launch. They docked to the space station a few months ago, And so starting this month, we're going to be paying private industry to deliver hardware to the space station. This is huge. There's a lot of people in NASA that just makes their skin crawl. I love it personally. So with that way long introduction, I'm going to start talking about, well, one more preface thing. About a week ago, I got my hands on a document that NASA headquarters had put together to actually try to describe, the new paradigm of how we're going to explore space. And so this talk is almost completely stolen from that document. I actually cut pictures out of it. I used a lot of my own words and found some of my own pictures, but this is a government document. So here's the document. I'm not even sure where you get it. Somebody sent it to me, but I bet if you Google that number, you'll be able to get your hands on the document that I'm talking about here, and it has a lot more detail in it. So the trick we're trying to solve is, how do we make space travel sustainable and actually affordable? Because it's got to be affordable or it won't be sustainable. And that's what this is about. So starting really in the last couple of years, somewhat quietly, because there's a lot of fighting in Congress over who gets funding to do what, NASA is attempting to ensure that the U.S. develops safe, robust, which means very active, affordable, that's the hardest part, and sustainable, flexible space program using a different paradigm. Instead of building something that's only good for the moon and going to the moon, where you spend billions of dollars to create an infrastructure on the moon, we want to develop evolving capabilities that could perhaps be used anywhere. And that's the trick. So here, what you're going to see is a few things where substantial technology development that's very risky would perhaps be done by NASA. But once things become a little bit more routine, industry ought to take over because they know how to do it much more efficiently. That's the paradigm we're shooting for. Not everyone in NASA would agree with that, by the way. So I keep emphasizing that because, like the people that are down the hall from me would, they would rather I'm not here and they get to give this talk because they tell you a different story. So there's a lot of discussion about that. So why do we explore? This is one of the fun questions. I know a guy at NASA headquarters that is spending full time actually trying to quantitatively answer this question. It's really hard. Why do people climb Mount Everest? It's a pretty stupid thing to do. You can die pretty easily climbing Mount Everest, but people do it. So there's sort of emotional, thrilling reasons for doing these things. People are curious, but like exploration in the past, certainly in the early decades of our own country, exploration of the West was driven by curiosity, but certainly many people went west for a better life. Find some farmland, make a living where they weren't working for somebody else. Economic expansion, certainly a lot of the West was settled because there were natural resources to go harvest and sell, ranging from wood to gold. And national pride, the Apollo program going to the moon was all about national pride. We needed to beat the Russians. Well, that doesn't really sell quite so much anymore, almost any of those things. But one of the things that we can see is that space exploration, it almost always teaches us something. Sometimes it's useful, sometimes it's maybe not as useful, but it always teaches us something about how our planet works or how it was formed, which is often useful to know. Something about the solar system, how it was formed, and sometimes even about ourselves, how we may have evolved and developed over long periods of time. But one thing that certainly happens, every exploration activity that's gone on has always developed new knowledge and new technologies. And you can extrapolate back hundreds of years for exploration. There was always new technology that was really coming out of exploration. It might have been a better ship to cross the ocean, but now it's better communications, better electronics. We invented Tang. Does anybody here actually know what Tang is? Okay, so that's really not entirely true, but NASA claims credit for stuff like that. So there's a lot of reasons for exploring. The reason that I've really been trying to to elucidate in the work that I've been doing is that I think the reason to explore is commercial. I think there's money to be made and there is value to be made in these exploration activities that can be brought back to Earth and make our life better here. It's not just about who gets to go hang out on Mars and who gets to go to an asteroid. It's we're going to make life better here because of the technology we developed to explore. And I think that's the reason to spend money on it. So if we're going to develop capabilities to explore, I want to talk real quickly about the different destinations that are being examined. And of course, a bunch of, you may know of most of these, but there's individual reasons for why one might do this. So we have the International Space Station. We've spent a great deal of money to put it up there. We spent, on the order of, some estimates range up to $1 billion per launch of the Space Shuttle to get to the space station. The Russians also supply the space station with cargo ships. The Japanese supply the space station with cargo. And the Europeans supply the space station with cargo. So there's a lot of ways to get stuff up to the space station now. But what do we use the space station for? What should we be using it for? It's a zero gravity environment. So, the moon and Mars is not zero gravity. So it's not quite the same thing. And there's a lot of differences there. But on the space station, we really want to use that opportunity to study how physical and living systems behave in an environment that's different than on the surface of the Earth. And it's different. The most important thing that's different is the gravity level. But there's other things. You have a constrained volume. People have to live together for months on end, so they have to get along without, getting angry with each other and living well. They have to figure out how to give each other first aid if something goes wrong. They have to solve problems without being able to drive to Home Depot to go buy a screwdriver to fix something, because it's really expensive to get something up to the space station. So everything has to be planned well in advance. But in addition to sort of understanding how physical systems and living systems work, it's a perfect test bed for developing the technologies that we will need to go elsewhere. We can study how gravity affects things and then design new systems to adapt them to the gravity level on the moon and on Mars. So I have a couple of pictures here, and I know I'm going to run out of time, but we are growing plants on the space station to learn how gravity and the radiation environment in space would affect them. We certainly are doing all kinds of studies of human physiology because reduced gravity tends to allow your bones to be not stressed, and so they lose calcium and they lose strength. And this is why astronauts that have been in space for a very long period of time, when they come back, their bones aren't very strong anymore. Turns out women are a little bit better at that than men. In case any of you young ladies out there, you don't play football, but your bones will last longer in space than men typically. Shannon Lucid, one of my favorite astronauts, came back from the Russian Space Station MIR after a record period of time, and she was walking around, and a lot of the male cosmonauts really aren't able to stand. So they're still trying to figure out what's the difference there. We are learning, there we go. Something that I did for many years was study how combustion processes work on space, learning how to prevent fires. This is a photograph of a burning droplet of a liquid fuel. And the work that we're doing here, the numerical modeling that goes behind this is actually being used in the codes that predict the performance of droplet burning in aircraft engines. So stuff we're doing in space is actually finding its way into terrestrial technology. It also makes pretty nice pictures too. The group that I'm working with now, we're actually sending samples of materials up to the space station to see how the radiation and vacuum environment affects the materials when they're outside the space station, not when they're inside with the crew. You may have heard that the Johnson Space Center developed something called the Robonaut. This is really an amazing piece of machinery. It quite well mimics the arms and the finger gesticulations of humans. And this thing has been flown in the space station primarily inside, so they're learning how to have astronauts and a human-like robot work together to do things, but the robot can do things that are very repetitive and save stress on the astronauts. In the next couple of years, they'll be deploying these things outside to do some of the tasks that astronauts have been doing outside the space station much more safely by having the robot do it. And one of my favorite reasons for the space station is because it gives us an opportunity to train the next generation of explorers. This is me on the KC-135. I got to do quite a lot of that. I flew, hundreds of times doing zero-G experiments, mostly with combustion tests. That was really fun. I got pretty good at it and didn't get sick, which a lot of people do, but not everyone does. You don't automatically get sick. And the reason I picked this picture is because the two students that were working with me, neither of whom ever got sick. This picture is probably, I'm going to say, about 10 years old. The guy that's floating on the left, almost upside down, is in the final round of selection for the astronaut corps. He was in the final round. The last go-around didn't make it. I just about guaranteed he'll be selected as an astronaut before the end of the year. And the woman that is between us is one of the chief test engineers at NASA Glenn, testing rocket engine technology in our facilities there. So I've had a lot of fun training these students and sending them off to do really cool things like I've been able to do. So this is, the space station is going to be a very good training ground. So one of the biggest challenges, a few years ago we were all pointed at going to the moon. And that's really good, but going to the moon has a real problem, and that is coming home. It's actually really difficult to launch from the moon with any significant amount of weight. It takes a lot of energy to do that, which means it takes a lot of propellant, which means you've got to land with all of that propellant, which means you have to launch all of that propellant from Earth. So to just get off the moon, it takes a huge amount of propellant in your great big rocket to get it off the ground on the Earth, to get it up into orbit, to get it to the moon, to get it down on the moon. So one of the biggest challenges is getting back off of the moon. Well, that's really hard and it's really expensive. So a lot of people were thinking, what can we do without landing on the moon, but still make use of what is called cislunar space? And cislunar space is just this sphere that's defined by the orbit of the moon. So it's the space between the Earth and the moon. So there's a lot we can actually do. We need to figure out how, because once you get far enough away from the Earth, you're outside the Van Allen belt, so there's a lot more radiation that's going to be affecting your health and the health of your hardware. That radiation will also destroy your hardware as well as yourself. So we have to learn how to do that, and so we can study that quite a lot in cislunar space. We have to learn how to operate spacecraft where they have to dock, they have to maneuver, and it's quite different when you're in cislunar space compared to when you're just going around in orbit in Earth. So all of the maneuvering to be done efficiently and perhaps autonomously, this is something we have to learn how to do. We have not done that very much before at all. One of the nice things that could come out from that is that, we put, billion-dollar satellites into orbit around the Earth, communication satellites, spy satellites, telescopes, etc. And it's almost impossible to go there and fix them. It's almost impossible to go there. It is currently impossible to go there to refuel them, because they need fuel, because they need to turn, they need to adjust their orbit, whatever. When they run out of fuel, they come in and that's it. And we could easily have a thriving business of refueling satellites if we could efficiently get the fuel to the satellite. But we have never refueled, put the gas, the nozzle in the gas tank. We've never done that in space. It's a vacuum, it's hard. We've never done that. We need to learn how to do that. And if we can learn how to do that for exploration purposes, we will revolutionize the communication and other type of satellite industry that's going on worldwide. Finally, we need to just practice for all the sorts of things that occur in deep space operations, but do it while we are still relatively close to the Earth. Near-Earth asteroids. Anybody not heard of a near-Earth asteroid? There's been some good movies about this sort of thing. So asteroids are mostly between Mars and Jupiter, but there's plenty of them that intersect the orbit of Earth. If one's big enough and it actually hits, we wipe out the dinosaurs, 65 million years ago. That's the prevailing theory of how that happened. But we really don't want that to happen again because, it would kind of mess up my backyard. So we really want to figure out how to avoid that. But there's a bunch of problems there. First of all, we know where about 8,000 of them are, but we're sure that there are many, many more of them. And it would only take something, like a kilometer in diameter to cause a huge amount of damage if it collided with Earth. And, they're hard to see if they're far away. So we have to find them. We have to figure out how to go there and do something about it, whether it's robotically or whether people actually go there and do something about it. But there's a couple of things. We want to figure out how to either, move them out of their orbit so they wouldn't collide with Earth or destroy them. That's probably not the right way to do it, but we need to figure out a way to mitigate the possibility that they would hit the Earth. There are also a treasure trove of scientific information because those asteroids really are the source material out of which the Earth was made once long, long, long ago. And so this is a way to study those dynamics. But most importantly, in my opinion, is those asteroids are a source of raw materials that would be extremely expensive to get into space. Most of them are made out of rock. Typically iron and nickel are the main metallic components, and we certainly could learn how to stuff them into some kind of manufacturing plant and make something out of them. But a bunch of them are actually made out of water ice. Now that sounds sort of boring, but if we didn't have to launch water off the surface of the Earth, if we didn't have to launch oxygen off the surface of the Earth, supplying the space station would be a lot easier. That's the main thing that we bring to the space station is water and breathing air. If we could harvest the water from these asteroids, we could make propellant out of it. You use electrolysis, you got hydrogen and oxygen, then you turn around and you burn it in a rocket engine. You've got propellant like that. You've got water and you've got air to breathe. So this is incredibly valuable. There is a new startup company called Planetary Resources, which is basically being funded primarily by the very wealthy people that run Google. And their 20-year plan is to first learn how to find out where all these things are, figure out how to get there, and thirdly, how to harvest them, actually capture it and bring this picture doesn't really work very well in this well-lit room, but this is a picture of an asteroid with a great big net around it, and they put a little propulsion unit on it and bring it back to near Earth and park it someplace and then eat it up and make something out of its constituents. I think this is a very practical thing to do. Not going to happen next year, but I'll tell you, if I was your age, that's what I'd be pointing for, is to do that. The people, when they solve that, they are going to be very wealthy people. If they figure out how to get raw materials into Earth orbit without having to launch it from the ground, they're going to be well set. The moon, basically the short answer there is it's a planetary surface once we can figure out how to get off of it, but the primary way we're going to get off of it is to use the resources that are on the moon to make propellant. The biggest deal that's happened in lunar exploration in the last few years has been done from orbit, robotically. I wasn't a big fan of how they did this, but one of the things they did was they sent a vehicle there with an orbiter to circle the moon, and basically has all kinds of instruments on it to detect materials remotely. And then on the same launch vehicle, but a little bit, I guess it was actually a little bit ahead of this sensor, they had this dummy vehicle that was about the size of a school bus, and they crashed it into one of these permanently shadowed craters near the south pole of the moon. These craters are at the south pole, so they never ever see the sun. It's always, always dark. And so it's like 40 degrees Kelvin. So before I'm done, somebody figure out what that is in Fahrenheit. I know the answer. So it's extremely cold. It's minus several hundred F. So they crashed a bus into this crater, and of course it made a big splash, and this remotely instrumented satellite basically detected lots of water, but it also detected a little bit of methane and carbon dioxide and silver and a bunch of other stuff, materials that had collected in what's called a cold trap. Once the stuff gets in there, it doesn't come out because it never vaporizes in the sunlight. So these very cold craters are a source of perhaps tremendous amounts of water. That might be where we get the propellant mass to get back off the moon. It might also be where we get the propellant mass to bring back and refuel satellites around Earth. It might also be the propellant mass that we use to go to Mars. So there's a lot of reasons to go to the moon and figure out these resources. So Mars, this is, for those of us that don't really believe that Star Trek is quite real yet. We might get there, but it's not real yet. Mars is about as far as we can imagine going right now in terms of a place where we can live permanently on a planetary surface. Someday, perhaps even within your lifetime, we may figure out ways to go much, much faster than we can go now. But until we do that, we're not going to another star without having many generations of people live on this spacecraft till they get there. So Mars is a pretty big deal. It's our next planet. People don't usually say words like that, but that's the way I think about it. Mars has an atmosphere. You know what an atmosphere? It has a hydrosphere. We now know there's plenty of water on Mars. It's just all below the ground. Cryosphere, there's ice on the polar caps. And there's a lithosphere, which means the dirt and the rocks. And that has evolved over time. It's a very good lesson for us to learn about how Earth processes proceeded over time. It's pretty clear now from very recent discoveries of the Mars rovers that there was once water flowing on the surface of Mars, so the planet has changed quite a lot. It'd be nice to figure out how that changed, why it changed, and are we headed in the same direction here, that sort of thing. But there is enough known about Mars to speculate realistically that people probably could live there. The atmosphere is mostly carbon dioxide. The pressure is about 1/100th of the pressure that is on Earth. But if we can collect the carbon dioxide there, turn it into fuel, which we could do with the water, do you think we could use technology for collecting carbon dioxide and turning it into fuel on Earth? Does anybody think that would be useful here? So I want to be the guy that figures out how to do that before I'm too old to care, because I think that's a pretty good marketing opportunity. I probably won't manage to get that done, but it definitely will be done by the time you guys are my age. Efficient ways to collect carbon dioxide out of the air and turn it into fuel is a major possibility for completely solving our energy problems, especially if we can use sunlight as the energy source for doing it. And on Mars, that would absolutely be the way we do that. We're already making some progress. NASA is working with a company that is based in Ohio called Battelle Memorial Institute. They have developed technology called microchannel technology. It's incredibly efficient ways to do chemical processing in extremely small size things. The device that's on top here is a carbon dioxide capture device. It uses materials called zeolites. It's not yet very efficient, but they're working on ways to make it a good bit more efficient using sunlight as the source, so they don't need to use a fossil fuel to drive this thing. But in addition to being able to capture the CO2, this device here, it's a chemical reactor. This is a quarter, so this thing is about that big. That can process enough carbon dioxide and water to produce fuel for an ascent vehicle from Mars over the course of 1 year. A device that size could do it. So this is still in the development stage. The thing breaks before they get anywhere close to operating it for a year. So there's a lot of problems to solve, but the technology is going to come, and we're going to be able to do these things pretty soon. One last thing about Mars that doesn't get much discussion. It is conceivable, and there's been some good science fiction written about this, the idea of actually so-called terraforming Mars, that is actually changing the environment, introducing plants that would absorb the CO2 or from the surface, emit oxygen, and over the course of a century or two, return the planet Mars to something that would be more easily habitable by humans. So the people that talk about this, they're either very excited about doing that, or they're skeptical about doing it, saying it's not feasible, but there's plenty of people that say, it's perhaps not ethical to do something like that. So this is a debate that I'm sure will play out during the course of your lives, and I suggest you think about it, because it could be a pretty big deal if Mars turns out to be a place that we could go live if we change it. Is it okay to do that? So, what I was supposed to talk about for most of the time, but I blabbed on about this stuff. I'll be as quick as I can. we really need to develop capabilities that make this exploration activity cheaper. And there's some key elements of that that are the most critical. Most important are the transportation and life support issues, because that's what's the most expensive. It's the rockets and the life support systems. So that capability needs to be made remarkably less expensive. We have to figure out how to very effectively and cheaply protect people and hardware from the effects of the very difficult environment in space, including intense radiation, heat, cold, vacuum, and low gravity. So all of these things tend to make life difficult for people and to destroy hardware over the course of time. And we have to figure out how to keep that from happening, or happening much more slowly. And of course, to explore in most places we want to go, the ability to resupply people from Earth is quite limited. So we have to figure out how to live off the land very reliably. So transportation, there's a couple things going on. I mentioned commercial cargo delivery to the space station. This is just the beginning. Elon Musk, the guy who is the CEO of this and basically the funder of this, he said that he's doing this because he intends to go to Mars. So his first step is to make a bunch of money delivering cargo to the International Space Station, and then leverage that funding to figure out how to go to Mars. If he figures out how to do that before NASA does, I'm okay with that. I'll go work for him. I think the commercial enterprise is probably going to be the answer here. Big debate going on within NASA, how much to fund this commercial activity. I think a lot of people that are in charge of the decision making at NASA are very much behind it, but the members of Congress and the senators from the states that build NASA rockets are not so much in favor of it. So that's actually where the tussle is going on. In addition to the commercial crew, there's also a crewed capsule. It's called Orion, and it's a multi-purpose crew vehicle. It looks kind of like the Apollo capsules, except it's considerably bigger and much more capable. The idea of this design is that it could be used to go pretty much anywhere in space. It would not be used to land on the surface anywhere, but it would be the habitat while in space. And then NASA is also developing a very large launch vehicle. This is the other half of the commercial crew. These are the two things that fight over the money. So there's a big rocket being developed that would be able to supply cargo delivery to pretty much anywhere in the solar system. So the one new thing that's going on most recently, and we have a very large role in that here at the NASA Glenn Research Center in Cleveland, a scant 40 minutes away from here, is something called solar electric propulsion. We have developed over the course of the last several decades some very high efficiency photovoltaic devices, and this continues to go on. There's tremendous innovations in basic physics that are making these devices considerably more efficient. Some of these photoelectric devices are now being commercialized. They are sufficiently efficient that they are being considered for actual, power grid, power generation to feed into the grid, not just for people to have on the roofs of their houses. But this electrical power would drive a so-called ion engine. So instead of having a chemical reactor to accelerate molecules out the back end of the rocket engine, you instead use an electric field to accelerate ions. Ions are much less massive than the molecules that result from chemical reaction. So you need vastly less propellant, and so you can have these things firing for months on end as long as you have the electrical power. It's something like 5 times more efficient. The energy that you expend compared to the thrust that you get out is something like 4 times more efficient than a chemical rocket. But people just haven't done it. I mean, we have flown these things, but they're this big and they have like 1 pound of thrust. We're now working on devices that would operate at like 30 kilowatt range, and then the next step would be 300 kilowatt range. These are orders of magnitude more powerful than the devices that exist now. This is probably how we would go anywhere besides to the moon. And eventually we would even use something like this to go to the moon. This technology is being developed in Ohio and in some companies, but this is happening now. The first flight of things of this size will probably be like 10 years from now, right about when you guys are finishing graduate school. You are all planning to go to graduate school, I hope. If you aren't, start thinking about it, because that's how you get to do stuff like this. All right. Habitats. Habitats are really tough. You have to protect crew from all kinds of nasty things. Currently, the only way to do this is you have to bring food, water, air, Game Boys, you know, whatever from Earth. And when you're on Mars, that's not going to work out economically. So we have to figure out how to recycle the air and the water, particularly, and any trash products that we're using to recover the materials from those and then reuse them. We can hopefully eventually live off the land, but part of that answer is recycling what we have. And we are working on technology now at NASA Glenn to actually figure out how to decompose plastics and recover the carbon atoms that are in those plastics to make propellants. I think this is part of the answer for coming back from Mars. So there's several technologies that are involved in making habitats work for the long haul. So destination systems, these are the sort of things that will work on a planetary surface other than the habitat. One of the most difficult things right now on the International Space Station is when the crew needs to go outside to fix something, like kills a whole day. They have to spend hours pre-breathing higher oxygen content than normal air because the spacesuits operate at a low pressure. And if any of you have ever done any diving where you go down in the ocean and then you can't come back up too fast because you get something called, exactly. And so if they don't pre-breathe oxygen before they get into these spacesuits and go outside for several hours, they are at risk of getting the bends. So there's a bunch of technologies being done to make these spacesuits operate at higher pressures so that they wouldn't have to do that. But another one of the problems of getting in and out of these spacesuits, it takes a long time. You got to have somebody else standing there, you know, putting everything together, making sure everything's sealed. At Johnson Space Center, they have developed these things that somebody can get into by themselves. They actually just crawl into it. It's like mounted on a wall. You just crawl into this thing. If anybody's interested, come up after. I'll show you the photograph. But they can just kind of climb into this thing, and then they close it up behind them, and then it just detaches from the side of the vehicle. So here they're crawling down into this thing on the inside, and then once they're done, it just breaks away from the side of the vehicle, and they can go walking away. And this takes you know, a half an hour instead of 2 or 3 hours. We've also developed, this was during the phase when we were spending a lot of time worrying about the moon. This device here, it's basically a very complicated vehicle that can go all kinds of directions, climb up hills and go sideways, but it's got a habitat sitting on top of it. Actually, on the back of that is where that suit deployment port lives, but that can also be used as an earth mover to actually contour the surface, so we can manipulate the surface. The device here is a plant that we built to actually process the lunar soil, which is basically crushed up rock. We can extract oxygen from that using hydrogen, heated hydrogen. This is a process that has to operate at about 900 degrees C, so it's pretty hot, but it's simple to do. The lunar soil, just like any rock that you pick up outside, is about 40% oxygen. So it's you know, as long as you can generate the energy to heat the rock, you can extract oxygen from the soil. We could extract oxygen from the rocks outside here if we thought we needed to do that. We haven't needed to do that so far. Another thing that's difficult on the moon is it gets really cold at night. Even if you're not in one of those permanently shadowed craters, it goes down to about minus 100 degrees C. That's really cold. So one way to ameliorate that problem is to use sunlight during the day to heat up rocks that are on the surface. Just like in the desert, lizards will spend the night on a rock that's been heated up by the sun during the day. We want to apply that same technique on the moon, and it works pretty well. coming in for a landing here. Okay, so kind of in summary, the capabilities to explore right now, it's way too expensive. I mean, it's not even close. We will never get the budget that we need out of any Congress, even if they all lived in Texas. They would never give us the money that we need to do this. So everything in our vision of space exploration, it's in addition to figuring out how to keep that from happening, it's going to require new technology. Most of what we need is new. We don't have it. We got to figure it out. It's going to happen in the next decade, so you'll get to participate if you point yourself this way. It's going to require international cooperation. We have a lot of things going on with various international partners, and there'll be more of that. And I think that the only way that we're going to get the investments that we need is if the technology developments that we're seeking also have terrestrial applications, among which are things like carbon dioxide capture, figuring out how to make people's bones last longer. There's a lot of applications of these technologies on Earth, and I think that's the only way we'll get funding to do this thing, including not only from the government, but from industrial concerns who are willing to invest in those terrestrial applications. So it's kind of interesting. I've been doing this talk for 3 years. Each year, there's been more images on my talk that were artist conceptions, and now are pictures of hardware. That's kind of cool to see, just over the course of 3 years. So I expect that trend to continue. I hope to keep coming back and talking about that more. Certainly there's new space propulsion. Clearly my focus is on developing technologies for harvesting natural resources elsewhere, and a lot of new material problems will arise. So there's several talks in this symposium about materials development. Almost all of them are applicable to space exploration. So, one last slide about how you can participate. I encourage you to consider learning not one discipline, but multiple disciplines, and then figure out how to make them work together. That's where the interesting stuff happens, is between disciplines. So that's something to consider. You have to learn how to take advantage of all of this information that is available to you, and you guys have massive amounts of information available to you without even having to walk through the snow to get to the library, like I had to do. So get good at that, and get critical about it, because there's a lot of junk on the internet too. I'm sure people have told you about that. Learn how to collaborate, because none of this is going to happen their teamwork is essential, and learn how to be international. Some of my best collaborators don't speak English very well, and so you have to figure out how to make that work. And I think most important of all, you're not used to flunking a test and walking away from it unfazed, right? Nobody likes doing that. Well, when you're doing something new, you're going to fail once in a while, and don't be afraid of that. Try stuff that's new. If it fails, say, okay, learn from it what you can and move on. But most people that have been successful have also failed more than once. So don't be afraid of that. And to the extent that there is time left, I'm willing to answer questions as long as you keep throwing them at me or don't get kicked out. Thank you.